So I will try to motivate. My talk will be mainly on variational problem. And I will try to motivate why we need free probability. So the problem we are trying to study, without using free probability, I don't know how we could have done it. So let me start with some principle. In the calculus of variation. So assume let S be a non-empty set and F be from S to negative infinity plus infinity be bounded from below. So usually you look at, you encounter such a problem in the calculus of variation, and you want to know if this is a minimum. So the answer is often based on the following theorem. If we can find a topology such that for every alpha in R, the sub-level sets F is less than or equal to alpha is compact, then we have a minimizer. And so mainly when we have a variational problem, we need to guess what topology will be useful for us. And since this is a two-line proof, let me, and I'm not going to miss that. So proof. Set Kn to be the set where the f of f over s is less than plus 1 over n. Then Kn has a finite intersection property. If x belongs to the intersection n from 1 to plus infinity of Kn, then S minimizes F over S. And so we see that no matter what variational problem we have, the main difficulty is looking for a topology which is going to be useful for us. So it will happen that I want to give an example where this variational principle failed, and there were mainly that appear in optimal transporter theory, although maybe this is not how originally the optimal transporter theory was taught, but you can summarize what is done in the following way. So example, when the above cannot be used directly. So sometimes this is a French translation. Probably English I would say cannot be used directly. So let H be L2, 0, 1 to the power D, RD. Let phi 1 be in C1 of RD. Phi 2 be in C1 of RD. And phi 1 of X is greater than S squared. So I am not assuming any convexity assumption. I am assuming just continuity. Set f of x to be the integral over omega phi 1 s of a dA plus the integral over omega phi 2 of s of a minus s of b dA dB. And try to find a minimizer. Yes? So set omega to be 0, 1 to the power d. And try to find a minimizer directly. When you look at the level sets, the natural topology is a weak topology. But if I don't impose any convexity condition on phi 1 and phi 2, the weak topology will be useless to have such a property. So what was done in optimal transport is introduce a quotient relation as follows. If x0, x1 are in H, S0 equivalent to S1 means that the law of S0 is the law of S1. So call this rho. By what I mean is rho mu. Mu is a measure on RD such that mu of any set of B equal to the Lebesgue measure of x0 inverse of B. So when you write the Hilbert space quotiented by this relation, you get the set of F such that F is from omega into R union plus infinity is convex and lower semi-continuous. Right. So this is mainly what is done by. I don't know if I can move this. I cannot.
The table's there. You can look.
No.
Okay.
It's okay, don't worry.
So if I have a converse function, here is my gain of complexity. If I take a omega naught subset of omega, if I have a converse function, the Laplacian of f, the absolute value over omega naught, is the integral over omega naught, the Laplacian of f. This is, I use the divergence theorem. This is the integral over the boundary of omega of the gradient of f inner product, the unit normal, and this is less than a constant, the integral over omega of the gradient of f. So I gain compactness for free, because if I take any bounded sequence here, it is BV, it converges almost everywhere. And in fact, I have a better than that. I have a convergence in LP for every P locally. And so, hence, the set of X, the set of X in the quotient space such that f of X is less than or equal to alpha is compact for the L2 topology, the strong L2 topology. So this may look like a sophisticated argument, because here I am relying on optimal transport to say that there is a one-to-one relation between between this quotient space and I am saying that it is not just that one set is contained in another set, right? It is clear that this is contained here. But I am saying that we have equality because I am relying on mass transport. But assume that I did not know any mass transport, but I have several decades of probability. I want to use very simple argument from probability. You can show this is what the probabilist has been doing for years. This is isometric to P2 of RD, the set of probability measure on RD with a finite second moment. And on this set, if I take anything such that the second moment is finite, this set is compact for the narrow convergence topology. And so I gain compactness easily. So we face some problem in the non-commutative case. And the only way we saw how to deal with that is to apply this principle where you use a quotient space. So let me start with why I want to study some class of non-commutative. Motivation. Game on MNC self-adjoint to the power D. So I take the set of n by n matrices with a complex entry, and I consider the one which are self-adjoint. So this is a particular case of Hilbert space. The theory of Hilbert of Hamilton-Jacobi equation. On Hilbert space is well understood, and its connection with dynamical game is also well understood. So there are some games which are evolutive dynamical game, and if you want to find a Nash equilibrium for that game, you solve a specific Hamilton-Jacobi equation, and if there exists characteristic in this for this Hamilton-Jacobi equation. You can show that you have existence of Nash equilibrium. So I am going to write the Hamilton-Jacobi equation in the characteristic in a few minutes. And so looking at this is just looking at a particular case of a very well-developed theory. So in a mean-field game, Pierre-Louis Lyon, Lasserie and Lyon, they propose this game where you have a certain number of players, and each player has his own noise, individual noise, and there is a common noise which acts on every player. So you can view this as each player move and have some randomness, but one institution is having an impact on all the players, and it has its own randomness, which all the players see the same way. So I will need some notation. Now I have a new omega pt, pf. Is a probability space. And 0t is the time the game lasts. So I am going to denote by Laplacian hat Mn. So the following is important. If I take a d equal to 1, all I am doing is going to reduce to the classical case. So I am mainly interested in the case that d is greater than or equal to 1. So denote by, let me start here. The Laplacian on Mn self-adjoint. But the Laplacian will be with respect to the normalized trace equal to 1 over n, the trace. So the process denotes by W hat n j. I want a d processes, j from 1 to d. So for each j, this defined from 0t cross omega into Mn, see, self-adjoint, is the process associated to the Laplacian. And for those who are familiar with it, it is called the GUE process. And you can write explicitly what it is, but it doesn't matter that you know how to write it explicitly here, because what matters is it relates to the Laplacian.
It starts from 0.
It starts at 0, yes. And so for each one of the players, I will have a GUE process. And then I am going to introduce, let W naught, which is independent of n, from 0 t cross omega to r, be such that W hat n 1, W hat n d, W naught are independent. So I am going to assume that I have given myself a running cost, which we call Lagrangian data. I am given Ln from Mn of C to the power d self-adjoint, cross itself into R. And I'm given a terminal value, Gn, from Mn of C to the power d self-adjoint to R. So this is my running cost. And this is my terminal value. And define V hat n from 0 t cross Mn self-adjoint to the power d into R by V hat of T naught S naught. So if I take T naught in 0t and S naught in Mn C to the power d self-adjoint, I am going to define this to be the infimum, the expectation, the integral from T naught to T ln, the infimum over x and alpha, ln st alpha t dt plus d of st subject to the following constraint, that S is defined by the differential equation for each component, alpha j t dt plus beta f. So I am going to assume that I am given parameter beta f for free and beta c for common noise, such that beta f d w hat n j t plus beta c dw naught. Remember, this is a one-dimensional Brownian motion, and so I multiply that by the n by n matrix. So here I have a skew-symmetric matrix with all entries full. And here I have a matrix where all entries are 0 except on the diagonal. And I am going to impose that S of T naught equal to S naught. So what I have done so far is very, yes?
The independence of W0 with respect to other Ws are mapping to matrices, but W0 is scalar problem.
It is scalar.
So there is an identity matrix in front of it?
This is why I multiply by the identity matrix here.
Okay, and there as well, or?
No, it doesn't matter. It doesn't matter. He's asking if for independence it matters if you multiply by identity or not.
For independence.
It just means all the entries.
Yeah, all the
All the entries. So you take the upper part of the entry because they are self-adjoint, and then you take the diagonal matrix for the last one, and all of them will be independent. So here I am studying a smaller class of problem compared to what is in the literature, because in the literature, they will multiply this by a matrix, and so everything here will be included in a matrix, and so this is a very special case. So call this Vn. As it happened in classical mechanics too, you look at a system with n. Yes?
I just want to say there's also, I think, should be a condition that the alpha process is adapted to the correct filtration.
Yes, so I need to, I need to say that I need to impose some measurability condition on alpha, which I am omitting to do. I hope you appreciate it.
Thank you. But the betas are fixed.
Say it again.
The betas.
Yes, the beta are fixed parameters. So I can take them 0 if I don't want the noise to play any role, or I can take them positive if I want the noise to play some role.
They're just numbers.
Yes. So my question is, can we describe the limit when n goes to plus infinity of v hat n and the corresponding game? So let us start with some guess and see how far we can push them. Of course, I am tempted to replace MNC. I am tempted to replace MNC by BH. H arbitrary Hilbert space. And I am tempted to replace the normalized trace by a trace. And this is where I first encounter an obstacle, BH may be too big for me to be able to define a trace. So I am going to restrict myself to a smaller set of this where I can define a trace. And the appropriate notion for that is do a C-star algebra, which I am going to endow with a trace. So I will use the following definition. A tau is a tracial for Neumann. Algebra. So David recall that something I forgot to say, and which is very important, is this work is based on two papers. One with David Jekel, Aaron Palmer, Yonsing Nam, and Dima. And in fact, this has been one of the longest projects I work on in my life.
How long? How long is long?
So the second paper is 2.5 years, and the first paper is 2 years.
It's not too bad. Pretty fast.
So let us hope that NSF hear you, that it is not too bad to produce one paper every 2 years. So is a Feynman algebra means A is a C-star algebra. Tau is a faithful, and I am going to briefly explain normal state trace. So let me summarize what this means. It means that if I look at AB in A cross A squared, go to tau A star B, where this is the adjoint. I want this to be an inner product. And I want A goes to tau. So I am going to denote my inner product. I am going to use the notation AB L2 tau. Is continuous with respect to the strong operator, weak operator topology, for instance. So this is vaguely the property I want to recover if I don't want to write the complete list of what it means to be a faithful normal state operator. So I want to gain compactness, and I am going to do as David suggested. So it is not a big gain in the finite dimensional case. It becomes a big gain when I let n go to infinity. So define an equivalence relation on MNCD self-adjoint by S1 SD is equivalent to Y1 YD if there exists unitary such that Sj equal to U star Yj U for every j from 1 to D. So if I define lambda for P, non-commutative polynomial of D variable, define the non-commutative law lambda x of P to be the trace of P of S1 SD, then S equivalent to Y is if and only if lambda x equal to lambda y. So the second formulation has the advantage that you can write it in infinite dimension, whereas the first formulation is not a good characterization for the class of equivalence in arbitrary dimension. So most people working on nonlinear PD will tell you that if you are looking for a solution to your PD, it is very rare that you look for solutions which are polynomial or which are function of polynomial. 10 minutes. Thank you. So we are going to have to introduce a class of functions which are not smooth, to have the freedom to do whatever we want. So notation. Set W. This is the set of A tracial for Neumann algebra with separable redual. Okay, so this is equivalent to the following. If I start with A, I can look at the closure of A with respect to the L2 of tau inner product, where the inner product has been defined there. And this is L2 of A, tau. I can similarly do the same thing for LP or L1 of A, tau. And so what I am requiring is this set is separable. And the definition. A family of function f, A in W is tracial if for every A in W, FA is from L2 AD self-adjoint to R. And it needs to satisfy some consistency condition, because if I have a smaller algebra and a bigger algebra, Neumann algebra, I want to say that if the smaller is included than the bigger, the extension from the smaller to the bigger is consistent. And for every I from A to B, W tracial, W star embedding, FB equal to FA composition I. And similarly, LA from L2 self-adjoint D square to R is tracial if you write the corresponding condition. Now I am going to define an equivalence relation, which is what is going to save us for convergence. Let X be in L2A to the power D self-adjoint, Y be in L2B D self-adjoint. We say that S is equivalent to Y if the following hold. I can put both space in a bigger Neumann algebra, and I have my embedding IA, IB, if IA of X equal to IB of Y. So I am applying the function component wise. Once I have this, I can extend the notion of non-commutative law, which is defined by Voiculescu. If lambda,
Something wrong, I think, no? But you want for any function, right? Or something like this.
no, so I am taking S here, and I am taking S here, and I am taking Y there. And I said that I can send them to the same element in C.
Either exists, I see.
Yes, either exists. Yes. So if X is in L2 of A, D, self-adjoint, we define lambda X of F to be Fa of S. So because of this property, that definition is consistent. And you can check that if I impose that S is in L infinity of A, it coincides with the notion of non-commutative law. And you can also check that, so if you take the Wasserstein distance, which was introduced by Brownian and Viscosity, and you extend the Wasserstein distance to a larger class of law, you can show that it coincides with minimizing the L2 norm. You can check that the L2 norm on the quotient space. You can check that this is exactly what it is. So how much time I have left? 2 minutes? Okay. So I'll give you a 2-minute explanation. So we can state the following theorem. Assume LA, GA satisfy appropriate condition. Let X be in L infinity of A, D, self-adjoint, and X naught N have a operator norm bounded by R be such that lambda S naught N converges to lambda S in law. Then the limit as n goes to plus infinity of v hat n t s naught n equal to. So you take a guess, and this will be the wrong guess, the infimum alpha x, the integral, the expectation of the integral from t naught to t, LA of S alpha plus G A S T where dsj equal to a corresponding differential equation which I cannot write. So if you hope that when a equal to b, this will be the limit, unfortunately, this function which I wrote here is not a tracial function. To make it a tracial function, I am going to minimize over all the embedding from A to B. And I am going to impose that x0. I am going to impose that I of x equal to Let me write the result. I promise I am done. So it will be the infimum over I from A to B, VB T naught I of x, where VB. Now I can write, so the limit when n goes to plus infinity, v hat n of T naught S naught n equal to that. And now I can write what is VB. So if I set V B T naught Y, and then it will be S of T naught equal to Y, and it is better to change this notation. Yes, then that is correct. Then to make the function tracial, you need to take the usual value function, which is given by the classical Hamilton-Jacobi theory, and you minimize over the bigger Feynman algebra. So you will be looking for paths in a bigger and bigger set to achieve your minimum. I am going to stop here.